All right, hi everybody. This video was asked for, so this is chapter 24, problem 32. We got early black and white television sets used an electron beam to draw a picture on a screen. The electrons in the beam were accelerated by a voltage of 3 kilovolts. The beam was then, so 3 kilovolts, that seems important. So 3 kilovolts. The beam was then steered to different points on a screen by coils of wire that produced a magnetic field of 0.65 Tesla. And so the first thing they ask is, what are the speed of the electrons in the beam? So the electrons are going to speed up. So I drew a little diagram of what they were saying here. So here's the electric potential that gets produced. So I got from 0 to 3 kilovolts right here. You can say like parallel plates or something like that does it. And so like this would be an electron in there. And right, it's going to speed up through this potential difference and then eventually is going to reach some speed when it reaches the end of this plate right here. So yes, and then it'll go into this magnetic field, which that's what this is here, and that's where it will spin and turn around and things like that. So all right, so, okay, let's see. So we want to try and find the speed of the electrons in the beam. So speed with things like an electron moving through some electric potential sounds to me like energy conservation. So I tend to like energy conservation with electricity. To me, the easiest way to do it is to do the instead of saying the initial energy equals the final energy, I'm just going to say the change in energy is equal to zero. Um, because then I can basically say that's the change in this case electric potential energy plus the change in kinetic energy is going to equal to zero. And then if I rearrange this, this gives me the change in kinetic energy is equal to the negative change in electric potential energy. And then I could go from here. So uh, if the electrons are released from rest, so and then eventually they'll reach a speed that I'm trying to find out, v. So basically, right, the change in kinetic energy, there's going to be zero kinetic energy to start with, and at the end, it's going to have a kinetic energy of 1/2 mv squared. That's the mass of an electron. And then over here, we're going to have the electric potential energy. Well, let's see, something that relates, an equation that relates electric potential energy and voltage. So let's see, I'll write the equation over here. The electric potential energy is equal to the charge multiplied by the potential difference. So the charge we have here is an electron. So that's, I'm just going to say, is negative E, the elementary charge, where again the elementary charge is equal to 1.6 times 10 to the negative 19 coulombs. And then multiplied by the potential difference. The potential difference is 3 kilovolts, so that's 3 times 10 to the 3 volts. That's the potential difference part. Or here, I'll just write potential difference. That'll be easier. Like that. Let's see. So this negative cancels with that negative. What are we trying to find? The speed. So isolating for the speed, it's going to be the square root of 2 times the elementary charge times the change in potential divided by the mass of an electron. If I plug all that in, 2 times 1.6 times 10 to the negative 19 times 3 kilovolts, that's times 10 to the 3. Let's rewrite that a little better. What was it? Three times 10 to the 3? Yeah, 3 times 10 to the 3. And then divided by the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. Plug all that in. Sorry, where's my calculator? There it is. Let's see. 2 times the elementary charge times 3 kilovolts divided by the mass of an electron and then square rooted. And I get 1, 2, 3, 4, 5, 6, 7. So 3.25 So my speed is 3.25 times 10 to the 7 meters per second, and we're within the speed of light frame of so we're less than the speed of light, so that's good. That suggests that's a fair answer there. So hopefully that's correct. If not, yell at me in the comments. Okay, so there we go. We got that one. So what's the acceleration do they experience? Do they, meaning the electrons, experience due to the magnetic field, assuming that it is perpendicular to their path? What is the acceleration in units of g? So we're going to find the acceleration. So basically, let's see. I can use my it's a negative charge, so I'm going to use my left-hand rule. My thumb is the direction of the velocity. My fingers point in the direction of the magnetic field, and my palm points downwards. So this is going to feel a magnetic force downwards, and that means it's going to turn in a circle. So it's going to turn in a circle. So there's like a quarter of a circle of a radius there. I'll call the radius r right now. And so there we go. So and that the force that's causing the centripetal acceleration is the magnetic force. So let's see what we can do down here to see if we can find out what the acceleration is going to be. So here's part B. We're going to use F net equals ma. In this case, the force that's causing the centripetal acceleration is the magnetic force, Fb, and that's going to equal the mass of the electron times its acceleration. Let's see. And so FB, so we got a charge. A good equation to use for that is QVB sine theta. And that's going to be the mass of the electron times the acceleration. Let's see. Theta is the angle between the velocity vector and the magnetic field vector. Well, if the velocity vector points to the right, the magnetic field vector points into the page. It's going to be 90 degrees. Sine of 90 is just 1. And then I can get then the acceleration. So it's QVB over the mass of the electron. That's the acceleration. So let's see. Oh, and Q, that's the charge. That's the elementary charge. So we got the elementary charge. So that is 1.6 times 10 to the negative 19 coulombs. The speed, which is 3.25 times 10 to the 7. And then the magnetic field, they told us was 0.65. And then divided by the mass of an electron, 9.11 times 10 to the negative 31. So we get an acceleration of, again, plugging into my calculator here. Let's see, we got elementary charge times 3.25 times 10 to the 7 times 0.65 divided by the mass of an electron. And we get 3.72 times 10 to the 18 meters per second squared. There is no limit on acceleration. Acceleration, as far as we know, can be as large as you want it to be. So there we go. So what is that in terms of g? Well, remember, g is 9.8 or 9.8 meters per second squared. So basically what it's asking is how much of this would that acceleration be? To make things a little bit easier, I'm just going to say 10. So I'll say 10 meters per second squared. So if I divide that, then that'll just take a little bit out of here into 17. So in terms of g's, the acceleration is 3.72 times 10 to the 17. Oh my goodness, g's. Yeah, if you're doing that, you're dead. Okay, let's see. Let's go on to C. If the electrons were to do a complete full circular orbit, what would be the radius? So now they're asking us for the radius. So to do that, I'm going to expand on what we have here. So this will be for part C. I'll just keep doing what I did from beyond there. So we got the elementary charge times the speed times the magnetic field divided by the mass of an electron. The acceleration, though, what type of acceleration is it? Well, it's a centripetal acceleration. Centripetal acceleration, as we've seen before, is v squared over r, the radius. So that's on your equation sheet. A centripetal acceleration is just the speed squared divided by r, assuming it's going in uniform circular motion. which in this class you can always assume that. Let's see, the speed cancels out then, and we can isolate R. I think I had you do this in class, but regardless, we'll do this. So it's the mass of the electron times V. Interestingly enough, that's the momentum times the elementary charge times the magnetic field. So again, plugging all this in, 9.11 times 10 to the negative 31 kilograms. The speed is 3.25 times 10 to the 7. And then divided by elementary charge, that's 1.6 times 10 to the negative 19. And then the magnetic field is 0.65, I think. Yep. So plugging all this in, mass of an electron. Where's my mass of an electron? There we go. Times 3.25 times 10 to the 7 divided by the elementary charge times 0.65. So I'm getting a radius of 1, 2, 3, 4. So 2.84 times 10 to the negative 4 meters. And there we go. That's the radius I'm getting. Again, hopefully I didn't make any mistakes. And then lastly is, so we did this, now we're getting into D. Magnetic field can be used to redirect the beam, but electrons are brought to a high speed by an electric field. Why can't we use the magnetic field for this task? Well, if you see, the magnetic field always produces a force that is perpendicular to the velocity, right? The velocity is pointing to the right, the force points down. And that will always happen with a magnetic force. It will always point perpendicular to the velocity. Forces that point perpendicular to velocity are what we call quote unquote centripetal forces. So the magnetic force on a moving charge in classical physics only can change the direction of the charge. It cannot speed the charge up or slow the charge down. So in order to speed the charge up, to get it to that speed, we need to use an electric field. So that's essentially why. Okay, hope that helped. All right, thanks. Bye.